so it's a good time to start. Last week I had the impression that I presented everything extremely too fast. So what I want to do today is, at least for the last part of the lecture that was presented last week, I want to perform a recap, a little bit long recap, and go slowly about all the details that, well, I said, we can do this and that and that. I was somehow really unsatisfied with whatever was going on. So if you understood completely everything what was going on last week, at least the first part of the lecture is not for you. Hopefully the majority of you feel that it's actually needed. So what we're doing right now, the idea is to go beyond mean field. What we achieved so far in this class from the start of the semester, this is already lecture number 5, is that we know that if you're taking a system with a lot of degrees of freedom, the average over part of those degrees of freedom, and then instead of using the local forces, we use the Ginzburg-Landau approach to build the effective Hamiltonian, and then we explore this Hamiltonian that is based on symmetry and analyticity, and etc., etc., etc. One way of solving it, which we have seen already 2 weeks ago, is the mean field approach. Mean field approach is saying the following thing. If we have a partition function, and this partition function is an integration over all the possible values of your field, dm, and here we have e to the power minus beta f functional, which is the Hamiltonian, Ginzburg-Landau Hamiltonian of the m. The mean field approach was find one single m that contributes the most to the Hamiltonian over here, and effectively replace all of this by this single Hamiltonian e to the power minus beta f of m hat. Where what is m hat? M hat is our mean field approach, or mean field value, the specific single value for the field. Just to remind you that this f of m, which is the Ginzburg-Landau Hamiltonian, was an integral, at least in the P4 field, k over 2, gradient of m to the power 2, plus t divided by 2 m squared, plus u divided by 4 m to the 4th. And we found one single m hat, and we used it. Okay, so this is the mean field representation. No matter what is the Hamiltonian, actually this will work. Sometimes we have a constant m. Sometimes this m, as you've seen in the homework assignments, sometimes this m can actually vary as a function of position. But the idea is still the same. Pick one specific function, just one, and replace all of this functional integration by this one single function that is plugged inside your Hamiltonian, perform the integration, and that's it, and you have the partition function. Okay. This was the idea of the mean field. Problem, yes?
The f of the m in an example.
dm.
Okay.
dm.
Okay. And this is an example for one.
This is a specific example that we mostly use in this class. It's called the phi 4 field.
Wait, no, shouldn't it be over dx?
dx, you're absolutely right, sorry.
The other one, yeah.
Okay. Now, the problem here is that there are always fluctuations. And this is the movies that I've shown you last week. That this eventually suggests that the solution of whatever you're doing, so the procedure goes as follows. You take a system, you average a little bit, not too much, you average a little bit, and then for those average values, which we call field, you construct a Ginzburg-Landau Hamiltonian, and the solution is always either 0, right, or a specific m hat. And that's it. That's the only solution that you can have. And then you might have a phase transition between those two. So this is the idea of Ginzburg-Landau. If you have a phase transition, the phase transition is due to this mean field approach. Now, in reality, what we see that it's not always true. In reality, we see that you have a phase transition, but the new phase is not a uniform description of the media. Even if you have a single function which is position dependent and not constant, the reality shows that it's not always like that. You have domains, you have Goldstone modes, when your projector, if your field is a vector, is actually slowly rotating because of this potential produces a Mexican hat type potential. So this approach is not so good. Absolutely not good. And what we've done in order to treat it or deal with it is to go and say, well, let's take this f of m and do the following expansion. This f of m, we'll call it f of m hat, which is the value of the Ginzburg-Landau Hamiltonian for the mean field, plus the second order expansion. So we expanded the field, we expanded whatever stood over here up to a second order. We neglected any orders that were higher, okay? And since it's a minimal value, you don't have first order at all. And this guy we called was f2 of delta m. So the idea is your m of x is your constant value plus some fluctuations, delta m. What exactly are those fluctuations? Well, going to be dependent on x. At specific x, you will have fluctuation small, and another x you're going to have large fluctuations, but you have fluctuations over this constant field, which is the mean field approach. And the thing that we've done next is to try and see what's going to happen with this f2. Now, before I even write to you what exactly this f2 and what is the expansion, I want to try and digest the idea of why at all it is valuable and important to perform this expansion. Because the expansion is on the level of the Hamiltonian, and the Hamiltonian is itself an integral, and still we have to perform some sort of functional integration. Okay, so let's try and walk this path slowly. Here I felt that I somehow lost you. Questions? Yes.
The m of the m average plus delta m together. Delta m of x. It's not delta multiplication by mx.
No. So delta of m of x.
So delta is a factor, and then m.
No. Delta is not a factor. All of this is together.
Okay.
This is the fluctuation.
Okay.
Okay. It's just how I sign the fluctuation at specific positions. So this is the fluctuation. Okay. Now, why it's important? Eventually, all comes down to the fact that we need to compute the partition function. Okay. So let's look on the partition function itself. Now, if you remember the class on statistical physics, okay, so the only way, at least how I taught you that, but you mostly find this also in any textbook, the only way how we treat partition function is by performing factorization. So whatever you want to perform, the way to compute a partition function is when you have many variables, many degrees of freedom, is somehow to factorize. That's the idea in statistical physics. You do something to your system, you look on this and in this direction, you decide that your particles are of this type, of that type, but eventually you want to factorize. Otherwise, you don't really know how to compute those partition functions. And in our case, this partition function is a functional integral, so you integrate over all possible realizations of M, okay, e to the power minus beta f of M. Okay, now, when you perform this separation over here, right, we have still this functional integral d of m e to the power minus beta f of m hat, okay, and also you have e to the power minus beta f, we called it 2 of delta m. You state the following, you say the fluctuations, well, if this is a constant or this is some sort of a solution, this is absolutely independent of the single value that I found before. I just have one single value, this can be the constant, this is my background, all right? And on top of this I have fluctuations, and those fluctuations are independent from this specific constant value, approximately.
So when you see m, we're supposed to take both the m.
So over here, what you do, you integrate over all the possible values of m hat, which produces to you a one specific value eventually, and you integrate over all possible values of delta mx at hx.
But if we have a spectrum of perturbations,
you integrate over everything. Okay? Remember what functional integration tells you. You start from 0 and you end at L. And this is your m of x. Okay? Functional integration tells you pick up a function, okay? Plug it inside the Ginzburg-Landau functional, perform the integration, you get one value. Pick another function, right? Plug it inside this functional, compute the integral, you have another function. And you do this again and again and again and again, then you put it on a grid, and actually you integrate over all possible values of this function on your grid. You remember I performed this regularization of everything.
Yeah, I get that, but the whole point of doing taking the mean field is that, okay, we have one major contribution, everything else is kind of negligible, but now we are adding the delta m.
Yeah.
And in delta m, we are back to the point 0 because we again need to go over a lot of.
I agree with you, and we'll get there. I agree with you. Yes.
So
yes.
Basically the mean field is an ideal case, and adding these fluctuations makes it more.
I'm not saying ideal. Let's call it simple case.
Simple.
Okay.
And
I don't know what's ideal here.
And adding these fluctuations makes it more
Realistic.
Yeah.
Yeah. Yeah. So the actually, you can say I'm looking physically on a system, and it's never a constant value. So you look on a ferromagnet, and it's never a constant magnetization everywhere. Say, well, there are small fluctuations, and the question is whether those fluctuations are indeed small and negligible, and you can throw them away, right? Or they're actually large, and we see that there are specific behaviors, Gaussian modes, domain walls. You've seen other stuff and kinks in liquid crystals. So there are tons of behaviors over there that are completely not described by the mean field. And our goal now is say, well, we have interactions, somehow mean field fails. How exactly it fails? Okay? And the physicists, when they try to understand something, the usual approach is say, let's push our theory, our system, a little bit out of this, not ideal, but the simple realization. And this is what we're trying to do now. And you're right, I need to integrate over all possible realizations of those delta m's. Okay? No, but before I do that, look on those guys. Now, the idea is, well, you have m, and you have those delta m's. Delta m's are different at different positions, and we perform this separation. The idea is to say m hat and delta m absolutely independent of each other. And if they are independent of each other, okay, I can factorize this integral. Okay. I can say, what is delta m? If they're independent, I integrate over possible values of m hat, and I integrate over all the possible values of delta m. Okay. So I write it down as d of m hat and d of delta m, because they are completely independent. So if I have to integrate over a two-dimensional space, right, I can say, well, what I'm integrating over, dx and dy. I'm integrating over dimensional space of different functions. One is a constant function m star with different values. Great. The other one, the different values of those delta m's. They are independent of the value of m hat. So what the hell? I'm just taking this differential and writing it as a multiplication. So what it brings us to? It brings us to that z equals to an integral over d m star e to the power minus beta f m star, which is a constant, multiplied by an integral of d delta m, all the possible delta m's in all the possible delta x's, of e to the power minus beta, what we call f2 delta m. Okay. This is exactly factorization, right? This is exactly factorization, because I know what this guy provides me. We've done it. This is a mean field approach. It just gives me one specific value. That's it. This is a saddle point approximation. You assume, oh, I take a mean field which is constant or as a single function, and I can shift it up, shift it down, but I have a single parameter, right? And by using the saddle point approximation, assuming that my volume is large, I'm doing a macroscopic, treating macroscopical system. So this is simply e to the power minus beta f of m. Proportional. There is some constant over here. But there are those guys. Those guys are here, right? This is an integral d delta m e to the power minus beta f2 delta m. So as you said, mean field was wonderful. It brought us many different interesting behaviors, but it's only one part. The moment that we add fluctuations for the partition function, there is another multiplicative stuff that is sitting over here somehow. Okay, this is the contribution of those fluctuations, large, small, who knows, right? We don't really know.
Can I ask another question?
Sure.
That might different complicated. So, like many times, fluctuation in, for example, the solid material is dependent on the temperature.
Yes.
So you have a double dependence, like in the exponent.
Yes.
What do you do then?
But it was already the same question you could ask me for the
yeah, of course.
for the mean field solution. So I
but
will.
here we assume this is a constant.
So what?
So if it's a constant, we don't really consider any fluctuation. The temperature gives us like a
No. So if you go back, so what is the question is? I have the effect of the temperature, and the effect of the temperature when we treat simple systems like in statistical physics. Okay, the only effect of the temperature always enters through this beta over here. I remind you, beta is 1 over k Boltzmann T. And whatever energy over here was not dependent on the temperature. But, and this is why in the Ginzburg-Landau approach, all of those values, remember k and t and u, can depend on the temperature because we average it. Okay? The moment you coarse grade over some degrees of freedom, effectively those guys can depend on temperature. So you don't care if it's double dependence on the temperature. It's already not the simple representation from the statistical physics where the whole dependence on temperature sits over here. It's not true. Even for the mean field approach, the temperature sits over here. So what is if it's constant? It can depend on temperature. How exactly? I don't know. We have to solve it and see. For the mean field, we've seen that T was equals to T minus Tc. So what?
No, I think that, but then we have like M outside of the energy, because B, if we go to the classical.
You asked me, so the delta M is going to depend on the temperature. Yes, and we'll see how. Yes, 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 yes. Yes.
Are there memory, like, can those functions be dependent
No
on
time dependence yet. So the class is still, we are treating equilibrium statistical physics. The moment that I will finish the ideas of renormalization group, hopefully we'll finish it by the end of the semester. So the plan was to finish renormalization and then go to non-equilibrium stuff, or the approach to equilibrium, and then there's going to be some time dependence. Right now, you look on the system at equilibrium. No time dependence whatsoever. Okay. Any other questions? Great. Okay. So look on this. The Z is a multiplication of something, which is a mean field approach, and another guy. Okay. Great. So we can treat separately the mean field solution, and we can treat separately the Z of the delta M. Right? I can call it effectively, that Z is Z of mean field, right? Multiplied of Z of fluctuations. I managed to separate them. Okay. Now, here comes the question, what is this Z of fluctuations? Right? Now, I already cannot use this simple approach that I did for mean field. I cannot assume that the fluctuations are constant, right? Because if the fluctuations are constant, they should sit in the mean field solution. So the fluctuations have to have some other values. But in general, Z of fluctuations equals to integral of all possible values of what? Of delta M e to the power minus beta and what we called F2 delta M. Okay, and what is this F2 delta M? I won't repeat the derivation that I have done last week. But last week we obtained the following result. F delta M is 1/2 an integral of what we have inside K, a gradient of delta M squared plus M effective squared delta M squared. Wait a second. Space. This is Z. And here I have d dx. So let's assume we are treating dimension d. This is the small d over here. And this is what we developed last week. This is not the Ginzburg-Landau Hamiltonian. This is the corrections due to the fluctuations to the Ginzburg-Landau Hamiltonian. Okay. Or you can say the expansion to the second order over the mean field. Okay. We have a mean field. It sits over here. And you have this additional Hamiltonian, which is the correction. You can think about it as a perturbation over mean field, if you like. Great. Now, I cannot use, once again, this trick of mean field solution. I cannot say, oh, let's say delta M equals to some constant, because then the constant is in the mean field. Okay. So I have to do something. And what we managed to do is to say the following thing. We use the Fourier transform approach. We said the following. Let's assume that delta m x, and let's use x vector. Why? Because we are sitting in d-dimensional space and we can do it for any type of dimension. Is, by the way, before I will do that, I write to you what exactly is m effective. So k is the same k as the Ginzburg-Landau, and m effective squared, we found out that it is d plus 3u m hat squared. M hat is the mean field solution. So it's some specific constant that indeed depends on the temperature somehow, because this guy depends on the temperature and this guy depends on the temperature. Okay? So all of this somehow depends on the temperature. And we see that the Hamiltonian depends on the temperature, and we have another dependence on the temperature that comes from the 1 over k beta t. Okay? Yes. Yes. Okay.
But if m effective is in the free energy, doesn't that mean we can't do the multiplication of the two?
Very, very, very nice. So you set it as a constant, and then you can.
So we're both setting it as a constant and also not. Like we're
Not exactly. No.
we're doing the
So the answer. So I will say, what is the problem? The problem it tells us is that when I perform this factorization, I assume that m hat is completely independent of the delta m. Now, m hat that sits over here is all the possible values of the mean field, okay? But eventually I choose one, right? I eventually choose one. In order to perform this z of mean field, or to find this guy, I choose only one m hat, and that's it, right? Now, this one single m hat that I choose, this is the guy that sits inside the m effective. So the dependence ends when I choose one specific m hat. Otherwise, I cannot simply perform this separation over here. And the only thing that I'm saying, in this representation sits one single m hat. That's it. Okay, so it's a little bit tricky. It's not any possible m hat. Otherwise, those two guys, this guy and that guy, depends on each other. What this m hat here represents is the true mean field. After I performed the saddle point approximation and found one single m hat, and I put it inside this Hamiltonian. Okay? So in this Hamiltonian, in m effective, it's not dependent on the temperature. M hat. It depends on a specific value. And if you wish, you can write it down as minus 2t. Okay, so y minus 2t, if you remember what is the value of this m hat, and you substitute it inside, and if you write it in this form, minus 2t, it doesn't depend on the mean field solution, and you don't really care. Okay? Yes?
When you said that it is a single value, does it mean a scalar or can it be a function for x?
M?
For example, yes.
M hat?
Yeah, does it mean a single function or single value?
Great. So we're treating in our treatment here a single valued function. A single value, so a constant, basically, that can have many values. All right? But, as you've seen in your homework assignments, you can the mean field solution can have not a single constant for the mean field solution, but a function with a single parameter.
Yeah.
And you integrate over this parameter and you find a specific value of the parameter, right?
So
This is exactly the same thing.
So it can be either a single scalar or a single function.
A single function, and then you choose one parameter, and eventually you get a function, and that's it. Okay? The mean field solution eventually is choose only one single function and use it, and that's it. That's the mean field solution. Great. So we have minus 2t over here. This is our fluctuations Hamiltonian. And the next step that we have done is to say, I cannot use mean field, so I will use Fourier. And Fourier we have delta mx equals 1 over square root of the volume of the system, a summation over all possible values of vector, wave vector q, delta mq, which are the Fourier coefficients, e to the power I q x. Have it done. Okay. Okay. This is what we've done. So we did this, we plugged it inside our fluctuations Hamiltonian, and we obtained that f of 2 equals to 1/2 a summation over q k q squared plus an effective squared delta mq absolute value squared. This is what we obtain for the Hamiltonian. Why it's important to use this representation. So this is why, in the first place, we took only the second order approximation. Because the moment that we have second order approximation, if you substitute the Fourier representation, you will always get a quadratic contribution. Okay? If you had some other quadratic form of your Hamiltonian, you diagonalize, you place, so Einat, I hope, showed you, you use something that's called Haber-Stratonovich, blah, blah, blah. You always get a sum of quadratic something, now we call it delta mq squared, multiplied by the amplitude, a sum over all possible values of q. All right. So what are those guys? So this is the energy, right? Remember? This is the energy. And I have an energy, that looks like F2 equals 1/2 a sum over Q, A, Q, and here I have delta M Q squared. This is the energy of what? Harmonic oscillator. So I have a bunch of harmonic oscillators. So instead of saying, oh, I have fluctuations, and those fluctuations can be here large, can be here small, etc., saying all the fluctuations everywhere inside the space, their energy, this is how I build it, the energy is just a sum over different harmonic oscillators, and this AQ equals to KQ squared plus M effective squared is the amplitude of each oscillator. Okay. So basically say, take an oscillator. The oscillator is represented by some specific wave vector Q. Okay. The energy of this oscillator is just 1/2 AQ delta MQ absolute value square. And you have an energy contribution for this specific MQ. And how many MQ you have? Yeah, we have many different oscillators. Each of them contributes some energy to your system.
But then you can have a cutoff, which is nice.
You can have a cutoff, or even you don't really care of cutoff, because you will see something that this amplitude and this Q squared, you will see that you actually don't really need a cutoff.
Negligible?
Yeah. But you absolutely right. Why we have a cutoff? You had a system, right? And eventually you look on the different wavelengths inside your system. Okay, so large Q, they are proportional to small wavelengths, right? Now, but eventually you have to remember that you had a system that was discrete. You had a system that was composed of atoms, and there is a minimal distances between those atoms. So you have a minimal value of the wavelength that can actually survive inside your system. This means that you have a cutoff on your Q, always. Okay? Now, for our purposes, all right, for our purposes, what we want to compute, I remind you, we computed the mean field, and we want to compute this stuff. Okay, let's write it down. Okay, this is our factorization plan. We know that we want to compute z fluctuations. And z fluctuations was an integral over all delta m, d delta m, e to the power minus beta f2 delta m. Now, I can integrate over all possible values of m, of delta m, or since, well, each delta m is represented over all the different values of delta mq, instead of integrating over all different values of delta m, I will integrate over all different values of the Fourier coefficients. Right? So here I have d delta mq. Right? Instead of saying, well, I have this specific function that represents the fluctuation, I'm saying this function is described by a specific set of delta mq's. Then you plug this specific set of delta mq's inside this formula, and you have your delta mx. So when you sum over all possible values of delta mx, you basically sum over all possible values of delta mq. That's it. Okay. So instead of doing a functional integration over delta m, we do the functional integration over delta mq. Okay. Here we have e to the power minus beta, and instead of f2, we have a summation, right? Minus beta, a sum over q of fq. This is wonderful. Why it's wonderful? It's wonderful because, again, the only way how to solve partition function is by performing some sort of factorization. In order to perform factorization, I need two inputs. One, the energy have to be a sum over different entities. My energy, this is my energy, is a sum over different FQs. Great. The other input, all those entities have to be completely independent of each other. All those delta MQs are completely independent, right? I can vary delta MQ1 and delta MQ2 as I like. Okay? Nobody cares because I have to cover all possible delta MX. I have to vary all possible delta MQs, so they're completely independent when I perform integration. Great. This means that I can factorize everything. Z fluctuation is a multiplication over all possible values of Q of Z of Q. Okay. And what is Z of Q? Z of Q is an integral over delta MQ, okay, over delta MQ of what? Of e to the power minus beta FQ. So, what we have obtained, this is Z fluctuations.
Z of Q, right?
Where?
Fluctuation
Z of Q. Yes. Z of Q. Yes. Again, yes.
Aren't you summing over Q twice then?
No, why?
Because you FQ is defined as a summation over.
No, FQ is not a summation. FQ is this guy.
Ah, okay.
Okay? F2 of delta M is a sum over Q of FQ delta MQ. Okay? All right. What we have obtained, Z equals to Z mean field multiplied by a multiplication over all possible Q's. Okay, all possible Q's, ZQ. Hooray, hooray. Right, so if you go to the class on statistical physics, this is the goal, to represent everything by a multiplication of simple partition functions, and each of this partition function describe to you a single particle. Okay? This is a single particle for the mean field. It's not exactly single particle for the mean field, but we can use it as this. But you exactly know what this is. And this have a constant value, so you can say it's a normalization factor, if you like. Those guys, they describe fluctuations. And those fluctuations are just a sum or a bunch of harmonic oscillators, right? Those are the waves that sit inside your system, and you can describe the partition function of each and single one of them. That's it. Yes?
These are harmonic oscillators by construction, right?
Yes, because we assumed that we taking the Ginzburg-Landau and we take only the quadratic terms or quadratic description around the mean field. That's a very interesting question. What will happen if I'll take the third and fourth order, right? But it's another story. For now, it's at least tell us, okay, so you have a mean field solution, you have some fluctuations around it, and the assumption is that those fluctuations have to be small, right? They cannot be large in order to describe the system itself. Okay? So the moment that the fluctuations are enormous, you don't care about the mean field solution because the fluctuations ruin everything. They describe to you a completely different solution. The moment that the fluctuations are small, and you can take, oh, the oscillations of those guys are actually small, well, you don't really care about fluctuations. Those are the two limits. Okay, what is ZQ and how we treat it?
A Gaussian.
A Gaussian, great. But beforehand, we need to understand a little bit what is this. So all of here that was in functional integration, blah, 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 blah. This is eventually a single integral. This is a single integral, delta MQ. So what is delta MQ? We can say delta MQ has a specific value. It actually can have a complex number. So delta MQ is generally some AQ, which is a real number, plus IBQ. Right? Two numbers. It's a complex. It has a complex value. Well, in general, this is real, and I is I. So when I'm saying that I have an integral of minus beta FQ, over all possible values of delta MQ, what I'm saying that Z of Q equals to a double integral, because I have to integrate over all possible AQs and all possible BQs of e to the power minus beta AQ 1/2 beta divided by 2 AQ delta MQ absolute value. So, but D AQ D BQ. This is the partition function of each and single mode that I decided to include in my system as a fluctuation. Now, let's make our life a little bit easier. So if delta MQ is AQ plus IBQ, what is delta MQ absolute value squared?
A squared.
A squared, AQ squared,
Plus BQ.
plus BQ squared. Okay. So I have an integration, and here A and B can range from minus infinity to infinity, minus infinity to infinity. So ZQ, it's not just one single Gaussian, it's a double Gaussian, or integration over a double Gaussian. Integral from minus infinity to infinity, minus infinity to infinity, over e to the power minus beta divided by 2, AQ, okay, which is this guy, multiplied by a squared, multiplied by e to the power minus beta divided by 2, AQ, BQ squared, DAQ, DBQ. So I have a double Gaussian integral in order that describes for me Z of Q. Okay. So we can compute Z of Q, right?
Right.
What is the computation of Z of Q? So, right, so we have an integral of minus to infinity e to the power minus beta divided by 2 AQ squared DAQ multiplied an integration from minus infinity to infinity of e to the power minus beta divided by 2 AQ BQ squared DBQ. So just two Gaussian integrals. I remind to you that an integral from minus infinity to infinity e to the minus alpha x squared dx equals to square root of pi divided by alpha. Do you know how to prove it?
Yeah.
Hopefully. Okay. I think in my classes in probability and statistical mechanics I always show it, and I think it's enough.
It's part of the homework.
Sorry? It was part of the homework. All right. So we do this, right? The moment that we do this, so we obtain from this integral a square root of what we have.
2 pi
2 pi beta AQ. And for this integral, we also get a square root of 2 pi beta AQ. So in general, we obtain 2 pi, there is, 2 is fine, over beta AQ. So what we obtain, it is K 2 pi, K Boltzmann, T, divided by AQ, and AQ is K Q squared plus M effective squared. Very nice. So we compute this is ZQ. ZQ equals to 2 pi K Boltzmann T divided by K Q squared plus M effective squared. But this is not the interesting part, right? This is not the interesting part. Why it's not the interesting part? Well, the moment that I have ZQ, okay, you computed something, you can, what we've done with the partition function, we usually constructed out of it the potential, which is the free energy, and then we took derivatives, etc., etc. But this is not what we're interested in, okay? So bear with me for a little while. What we're interested in is the behavior of the fluctuations itself. Now, currently, we know only something about delta MQ. So we know that the probability of a specific delta MQ is given us by what? The 1 over z cubed e to the power minus beta. And what we have? Divided by 2, a cubed delta m cubed squared. This is the important part. We have the distribution of the Fourier representations of all the different of the distribution of the Fourier coefficients of the fluctuations. So it's a little bit far-fetching quantity, right? Because we want to understand something about the fluctuations. Are either valuable, not valuable, important, extended, not extended? What we managed to obtain is the probability distribution function, the PDF, of the Fourier coefficients. Okay? Yes?
למה בהתחלה שלך חילקת ב-Z של Q ולא ב-Z fluctuation? זה בעצם מכפילה על ZQ?
No. So the question, why it's Z over Q over here? So the moment that I factorize everything, I can treat each delta MQ separately. Okay?
כן, אבל ההסתברות היא על כל
No. This is the first part of when I teach factorization. You have a big bunch of the system. The moment you manage to factorize, you treat each and single one of them as the own system, and the Boltzmann factor and 1 over Zk applies to each single particle. Okay? This is why you factorize. The moment you manage to factorize, you treat each particle on its own. Okay? Otherwise, if I wouldn't do that, I would be stuck with a lot of different configurations of all the particles, and it's a dead end. This is the way to go. Okay? Other questions? What we do with that? So first of all, well, although it's a Fourier representations, etc., we can calculate pretty easily fluctuations or the average values of delta MQ. Now, I remind you, since this is the presentation, I can say the following. So this is delta MQ squared, right? There is no part which is linear inside the Gaussian. This means that delta MQ average equals 0. Okay? Delta MQ average equals 0. And I know that delta MQ absolute value squared equals to what? To AQ divided to whatever stands over there. So it is 1 over beta AQ. Okay. So if you're familiar with a Gaussian, if you have a P of x equals to 1 over square root of 2 pi sigma, and it's normalized, and e to the power minus x squared to sigma, so x, so the variance over x, it is just, this is squared, the variance over x is just sigma squared. So if you want to compute the variance, the only thing that you need to look on, what stands inside here. So you have x divided x squared divided by 2, and whatever is left is your variance. We have delta MQ squared, which is our x, divided by 2. Whatever is left is 1 over beta AQ. This is your variance.
Why is it 0 again?
Compute it. You want to compute it?
No, just computation.
Yeah. So if this is the guy, so x average equals to 0, because it's actually x minus mu squared. So x average for a Gaussian random variable, it's whatever stands inside. And in our case, nothing stands inside. Right? So the properties of Gaussian variables. This is why Einat told you that. Okay, so look, we obtained this, which tells us something about the amplitude, right? The amplitude of each mode. Because we represented everything by using modes. And we know now what is the amplitude of each mode of the fluctuations. Delta mq squared equals to 1 over beta, so we have k Boltzmann t, and aq is kq squared plus m effective squared. Great. Now, from here, you can understand, all right, so if this is the amplitude, think about it. I have a bunch of harmonic oscillators that describe to me the fluctuations inside the system. Okay. Now, each harmonic oscillator have an amplitude. This amplitude now, it depends on the temperature, but it also depends on the Q value over here. Okay. So when Q is large, what is large Q? Very fast fluctuations, right? Large Q, it's 1 over the wavelength that corresponds to the fluctuation. Large Q, small lambda, small wavelength, okay? And for small wavelengths, fast fluctuations, local fluctuations, this guy goes to 0. So this says that, well, if you have local small fluctuations, the amplitude of those fluctuations, at least in the Fourier spectrum, is going to be 0. What happens when Q goes to 0? Q goes to 0. What is Q goes to 0? Q is proportional to 1 over lambda. Lambda is the wavelength of the waves of the modes inside the system. What happens? Q goes to 0. Large wavelengths, so fluctuations over the whole distance, over the whole size of the system. It's not 0, right? It is k Boltzmann t divided by m effective squared. Yes?
Is it equivalent to putting a cutoff not in the Fourier space?
Oh, so you're asking me what is the cutoff for Q? There exists a maximal Q, but it doesn't really matter because even if Q is very, very large, this amplitude goes to 0.
No, but if we use the Fourier to find the cutoff,
Yes.
can we turn back to the regular expression and then say, okay, let's make it not an integral but a summation? Can we solve it this way? It's not elegant, but if the Fourier becomes too complicated or...
It's a good idea. I have to think about it. Any other questions? Yes.
Effective is temperature dependent. So what happens at TC? Because at TC those amplitudes divergent.
Yeah. So what happens at TC? The amplitudes start to diverge. Okay. So this is interesting. But when T goes to TC, okay, T goes to TC, M effective squared goes to 0. I remind you, this is minus 2t, M effective. Write it down over here. M effective squared is minus 2t. It equals to 2t minus tc. Okay. And otherwise it's 0. Okay. So what happens when you approach tc, M effective goes to 0, and you have 1 over q squared. When q goes to 0, the amplitude of those fluctuations explodes. Like, so something funky happens, but there is a hard transition in the head that you have to perform from, okay, this is the amplitude of what? Of some Fourier representation of the fluctuations, but what it means for the fluctuations in real space. Okay? So what we've done in order to represent, to make everything nice mathematically, we took fluctuations and we represented them by the Fourier transform And we now know something about the Fourier components of this transform and the distribution of those components. This is nice. But, well, maybe somebody who extremely familiar with the Fourier transform can tell me immediately what it means for the space Mx. Okay? So the thing is, well, it diverges, not diverges, something happened to it, etc., etc. Not clear to us what happens in real space. We understand what happens in Fourier space, but what happens in real space? And what I mean is, if we look on the system, okay, and we say, well, there is a background solution, and this is the mean field, and this is the mean field, okay, and the mean field solution can be uniform. And on top of this, we have fluctuations. Now, fluctuations, as we see, because delta MQ is 0, delta MX also probably 0 on average, okay? So what is delta MX? Is 1 over square root of V, a summation over Q, delta MQ, E, I, Q, X, right? So if I take the average of this, it's like taking the average of that. And this, there is an extremely useful phrase that you all remember. The average of the sum is
The sum of the average.
the sum of the averages, right? So 1 over square root of V, summation of Q, delta M Q, E I Q X. So this is delta MX. And if delta MQ equals to 0, as we computed over here, this whole sum is exactly 0, and delta MX is 0. So on average, fluctuations do not contribute anywhere. Okay, so you say, well, Stas, fantastic result. The fluctuations are not important, but this is not true. Because, well, here the fluctuation, if I take one realization, okay, it can be positive, it can be negative, it's not contributing. But, so here I had a fluctuation. But what happens in the point nearby, and another point, and another point, and another point? We know that domains are formed. So the question is, great, the fluctuation can be positive, a negative, and it's 0. But what is the correlations between nearby points? So let's assume that in each point you have one realization and the fluctuation was positive. You take another realization and the fluctuation was negative, and on average you have this uniform solution of mean field. But you can ask the following question. Okay, so now the fluctuation is positive. What is happening in the vicinity of this positive fluctuation? Maybe they are correlated, those fluctuations. And the moment they are correlated, this is why they create domains. And what is the size of this domain? Is it small? Is it large? If the domains are large and the values of the fluctuations are also large, you don't care about the uniform background. It's nonsense, right? You will have different domains of different shapes, and those fluctuations can be extremely large. Okay? And then the uniform background is completely unimportant. So it's not enough to compute this. You have to compute how the different fluctuations are correlated with each other. And this is the goal, right? I told you wonderful things about the Fourier transformation. It's true mathematically and it's very, very, very correct. But eventually the goal is to describe physics in real space. We use Fourier because it's nice, because you can diagonalize with the use of the Fourier. But eventually you have to go through real space and say, all right, what happens here? So I don't really know what those guys tell me. Well, delta MQ equals to 0 already told me about the fluctuations, but this is not what I wanted to compute. What I wanted to compute is the spatial correlations of the system, of the fluctuations. And what we want to do actually, so this was the recap of the last lecture. Was it useful?
Yes.
Okay.
Very much.
All right. I had this feeling. So what we actually want to compute is delta m x plus r average correlation function. Why is this important? Well, because if they are not correlated, if those guys are absolutely not correlated, then the size of those domains for any r, then the size of those domains are also zero. You don't care. It's only when I have a positive fluctuations in position x, it affects that in position x plus r, you're also going to have a positive fluctuation. Only then domains are created. If there are no correlations means delta m x plus r equals to delta m x plus r. And we know that this guy equals to 0, and this guy equals to 0, and in total equals to 0. So whatever happens in position x does not affect what happens on position y, x plus r, x plus 2, x plus 3, doesn't, and all fluctuates, no domains, nothing. It's only cooperation of fluctuations that creates something which is not mean field. So our question is, what is this guy?
Just the Fourier transform.
Mm-hmm. Very, 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 very well connected to this guy. So it's maybe not for you, but for everybody else. So first of all, you can ask, Stas, what is this r? So this function will depend on x. If the system is uniform, so everything is in one place, is very, very similar to another place, it should not depend on x, and the whole system should depend only on r. We only care about the distance, right? The correlations, how the different parts of the system affect each other, should only depend on the distance between the local fluctuations. So we want to compute g of r, which is this delta m x plus r.
Can I
Yes, sure.
You can write the correlation function in this form only when the system is translation symmetric, right?
Yes. So I'm saying it doesn't matter when I put my x.
Okay.
Right? So it translationally symmetric, or I'm saying it's in some sense it's uniform.
Okay.
Yes.
Should it not be also related to the direction if we have an external field?
If you have an external field, your translational symmetry is broken, then it's going to be dependent on the direction also.
Okay,
You're correct.
So
yes.
for now we assume no.
If we assume no external field, you remember we're still treating this phi for Ginzburg-Landau Hamiltonian without external fields. Okay, so how we're going to do this? We know something for the averages. We know something about what? We know something about the Fourier transforms. Okay? Because we know how the different modes are distributed. Well, we have it somewhere, okay, in my notes. So the way to go is to take this and represent it in the Fourier space. Take that and represent it in the Fourier space, and then take average when we know what's the average of the different Fourier components. So this is what we are going to do. Again, delta m x is 1 square root of the volume of the system, a sum over q1 of delta m q1 ei q1 x and delta m x plus r equals to 1 over square root of b, a sum over q2 delta m q2 e I q2, and instead of x, we put here x plus r. Now, we plug it inside this average, and we start to do a lot of algebra. Not that we haven't done a lot of algebra so far, but we are going to do a lot of algebra. Yes?
Does the volume stay the same for x and x?
So the volume is the volume of the system.
Of the whole system?
Of the whole system, yes.
So it's constant?
Yes.
We can ignore it?
Yes, if you like.
Okay.
You should have it. You see where it comes into place. You will see.
Okay.
You will see how it. You shouldn't just throw it out. Okay. You shouldn't.
And a delta function.
For exactly, we will have some delta function, and it should, and this affects the delta function.
Okay.
All right. So we have an average of 1 over square root of v, a sum over q1 delta m q1 e I k, okay, q1 x multiplied by summation 1 over square root of v, summation over q2 delta m q2 e I q2 x plus r. And we need to take the average for all of those guys. Okay, so we have 1 over v due to 1 over square root of v, 1 square root of v. We have a summation over q1. We have a summation over q2. We have here delta m q1. We have delta m q2. We have an average. And we have e to the power I q1 x plus I q2 x plus r. This is what we have. So in order to proceed, we need to calculate what is delta m q1, delta m q2. We know how to treat those guys. Why? Because we know what's the distribution of each and single one delta mq. And they are independent. So first of all, what do we know? We look on this and we say delta mq, delta mq1 and delta mq2 are completely independent of each other. So if q1 does not equals to q2, our wave vectors are not exactly the same, because those are two independent Gaussian random variables. Okay, we actually say those guys are independent. So the average delta m q1 delta m q2 equals to the average of delta m q1 multiplied by the average of delta m q2. That's the property of Gaussian random variables that are independent. But they are random variables, Gaussian random variables, with mean which equals to 0. So this is simply 0 multiplied by 0, and it is 0. So for any case, when q1 does not equals to q2, this guy equals to 0, and well, you don't care about anything. Okay, that's the regular case.
What does it mean physically that those vectors are not...
There is no contribution. What do you mean by physically in this Fourier space?
Like, one fluctuation...
So if you look on the fluctuations, the fluctuations of those harmonic oscillators are completely independent of each other. If you look in Fourier space, they behave independently. That's what it means.
That's why we assume that we have a correlation. So this
No. We have not assumed. We want to calculate the correlation.
No, here we assume that.
No, it does not assume anything. We want to calculate, and this is a correlation in space, and this is not space. This is Fourier, and we know that it's
They
zero.
are interchangeable.
Not exactly. How exactly?
If we have
This is the point of this exercise, right? I want to calculate the correlation in space. I don't know, while I know something about correlations in Fourier.
Is it not mathematically proven that we must? So for each to have a correlation, we have correlation in both spaces,
Not exactly. No. So you see that there is no correlation in Fourier space, but there might be correlation in, or maybe not. Maybe you're right. Let's see. Let's see. Bear with me a second.
It means that two spatial places will not have a correlation, that they're not in the same mode.
Yes.
Okay.
Yes. Okay. So what happens when Q1 equals to Q2? What happens here? So again, yes? Answer? Yes.
It's basically the average of the square.
Okay, let's see.
Which
Let's
we
see.
found.
So delta M Q squared, delta M Q, delta M Q average, which is delta M Q squared average, right? Okay, let's calculate this guy.
This is what we compute, right? Before?
Let's see. Okay. So I want to compute delta M Q squared. The average of delta M Q squared. It is what? So first of all, what is delta M Q squared? I remind you that delta M Q equals to AQ plus IBQ, where AQ and BQ are real numbers. So delta MQ squared equals to the average of AQ plus IBQ squared. Right? Okay. So what we have an average. Let's open the parentheses. We have AQ squared plus 2I AQ BQ minus BQ squared average. So we obtain that this is AQ squared average plus 2I AQ average BQ average minus BQ squared average. What is the distribution of AQ and BQ?
Gaussian.
Gaussian. So the distribution of AQ is minus beta over 2 AQ, so this is the probability of AQ, 1 root over 2 pi, and here I have 1 over beta AQ, and the probability of BQ is 1 over square root of 2 pi, 1 over beta AQ, e, this is squared, e to the power minus beta divided by 2, AQ, BQ squared. I remind you where this came from. This came from the probability of e to the power minus beta divided by 2 AQ delta MQ absolute value squared. And here I had 1 over 2 pi 1 over beta AQ. So this is a multiplication of those two guys. A small aq, and B small q, they are independent, and each of them have a Gaussian distribution. Okay, so using those, I can compute all the averages they have inside this expression. Again, it's the property of Gaussian variables. This is why in the class on probability for physicists, we spent 2.5 weeks teaching Gaussian random variables. And we expect you to remember this for 3 years. Okay, so what is AQ squared? Again, it's the property of random variable. So because you don't have any mu, any average value, okay, what you have over here, that AQ squared, is simply what stands below AQ squared. So this is 1 over beta and AQ. 1 over beta AQ, which is K Boltzmann T, divided by large K Q squared plus mu effective squared. BQ squared is exactly the same thing. 1 over beta AQ equals to K Boltzmann T, K Q squared, M effective squared. Average AQ equals to 0. Average BQ equals to 0. What I have obtained. What we have. What this average delta MQ equals to.
0.
Everything is 0.
Where?
Everything is 0.
Not really.
Not really. So where is the punch? Where I've hidden something.
Over there, when you took Q1 is not Q2, but if Q2 is minus Q1.
Exactly. There are correlations. There are correlations between Q1 and Q2. So I've hidden something. Indeed, when Q1 equals to Q2, this guy is exactly 0. And for most cases, when Q1 not equals to Q2, it's also 0. But there is a very special case. And what is the very special case? This special case is the following. I remind you, we have delta mx, which is real. It's a fluctuation in real space. It's not a complex number. It's real. And it is 1 over square root over v summation over q delta m cube ei q x. Okay. Now, what will happen if I'll take the conjugated complex value? Okay. So delta complex conjugated of mx equals to 1 over square root of v, a summation over all the possible values of q, delta mq conjugated, right? E to the power minus I Q X. But this is also equals to delta mx, right? Because real. Delta mx is real, so if I'm taking a complex conjugated out of it, it's still real. Where am I? All right. So what else can I say about it? Well, look on this. I'm saying, well, this is actually 1 square root of v, a summation. I can sum over q, or I can sum over minus q. Okay, I can sum over minus q, and I have here delta m minus q. We'll still have x. E to the power of I minus q x. Yes? Plus, I have plus over here, plus over there. Because the only difference is what is this guy is positive or this guy is negative. Now look, so this equals to that guy, exactly. Now, they both have to be real, okay? They both have to be real. And I say, but this equals to 1 over square root of b, a summation over q, delta m q, e to the power I q x. Delta mx equals to that. Delta complex conjugate equals to this guy. Right? Now I switched what is q and what is minus q. I called minus q my running vector, and then I have to put over here minus q. That's it. Okay. So we have this guy equals to that guy. And then, well, most of the time mathematicians prove existence and uniqueness. Awful things. Okay? Awful things. But they're useful, and specifically over here they're extremely useful. Why they're extremely useful over here? Because the Fourier representation is unique. The moment that you manage to build a function by using a specific set of Fourier coefficients, that's it. If you build another representation, those guys have to be the same. So uniqueness tells us that delta m cubed equals to delta m minus q complex conjugate. Let's take a complex conjugate of both sides. Okay. And we obtain that delta m q complex conjugate equals to delta m, here I have minus, I'm sorry, delta m minus q. There is one specific q. So you notice over here, q1 equals not equals to q2. Yes, q1 does not equals to minus q2, to minus q1. It's okay. But the moment that I put here delta m q1, and when q2 equals to minus q1, this assumption does not hold. Okay? So I have, this is correct, this is also correct, but there is one single case where it does not hold, this 0. And this is when q1 equals to or minus q2. And for this case, delta m q1, delta m q2 average equals to delta m q1, delta m minus q1. And according to what I've written over here, delta m minus q1 equals to delta m q1 complex conjugate. Delta m q1 delta m q1 complex conjugate, which is an average absolute value of delta m q1 absolute value average. This is the only contribution to those double sum which is not 0. Now, we calculate this, right? This is the amplitude of each single Fourier mode. So delta m q1 absolute value average equals to, we have k Boltzmann t divided by k q squared plus m effective squared. Okay, eventually. So I remind you where we are standing, what we've achieved. 2 minutes and I'm done. So bear with me for 2 minutes. We calculated G of R. And this G of R was 1 over V, a summation over Q1, a summation over Q2, okay, over what? Delta M Q1, delta M Q2, e to the power I Q1 x plus I Q x plus R. Now, what we managed to show is that delta M Q1, delta M Q2 equals to what? Equals to K Boltzmann T divided by K squared plus K squared Q, no, KQ squared plus M effective squared. Delta Q1. Delta Q1 minus, or delta Q2 minus Q1. Only very specific Q2 contributes. That's it. Now, you take this, you plug it inside, and it kills the summation over Q2. Right? We have a delta of Kronecker, which kills the summation. And out of this, we obtain that G of R equals to 1 over V a sum over Q1 K Boltzmann T divided by K Q squared plus M effective squared. Now here I have, this is Q2, so Q1x minus Q1x cancels out, and I'm left with e to the power I Q1R. So G of R is some sort of Fourier transform, this guys, or this is the Fourier coefficients of our correlation function. And the main question, what it equals to. The answer to this is another 6 pages. So we'll do it next week. Okay, thank you.
So in the week so far of the course, we talked about the Ginzburg-Landau theory. And specifically last week we added the fluctuations, and I want to start with like wrapping it up together like מסודר כזה, okay. Okay, so the Ginzburg-Landau theory is supposed to explain phase transitions. So we have Hamiltonian, which is a functional of some, suppose the order parameter, which is a field, and we want to calculate the partition function, which explains all the physics in statistical mechanics, right? And we started with the saddle point approximation, where saddle point, where the partition function is just goes like e to the power of minus beta times the minimal value of the free energy. And then we saw how to do mean field solutions. So it starts with some ansatz about what is the form of the minimal mx. So for the standard, I don't know, the magnetization Hamiltonian, it's just a constant m. And then we minimize the free energy and get an equation for T, which describes the free transition. Okay. So actually, this picture is accurate at t equals 0. Okay, t equals 0. But when t is finite, there are fluctuations which may have like no effect or major effect on the physics. So we have to also take them into account. Okay. Okay, so I think Stas did it on the lecture, right? But I wanna just do it slowly, or not so slowly, but just repeat it. So for magnetization, we have this Hamiltonian. And we have the saddle point. We did it many times. For mean field, we say that mx is a constant. And then the free energy is just and then we find the minima. And we have 3 solutions. M equals 0 and okay. So this is the saddle point, and now we want to add fluctuation. So we start with, okay, we say that mx is m0, which is like these solutions, plus some delta m, which depends on x. So this is the fluctuation. Okay, so it's basically like expanding around the saddle point. Okay, so let's I'll call it phi of x equals. I find it like easier to use, so I plug it into the Hamiltonian. m0 is constant. So okay, so now I don't want to open up all the terms. I'll start like with powers of 5, okay? Of course, sorry, that we assume that the fluctuations are smaller than m0. So phi is the small variable, so I'll start with the terms that don't depend on phi, and then we will go in the powers until we can stop. Okay, so from here we have m0 squared, and from here vm0 to the 4th. This is just f m0. Now to the first power of phi. From here we have 2a m0, and from here we have 4b m0 to the 3rd. Okay. Now this is exactly it solves the it's this term. Yes, exactly. So it's 0. So we have to go to the next term. So from here we have a, and here we have 6b and 0. Okay, so we can stop here. So we can integrate this out. We get and plus this. Okay, plus this, and we want, you can already see that it's going to be like a quadratic Hamiltonian, so we want to give it a nicer name, so we say it's k psi minus 2 phi squared. So okay. Sorry. So this is HM. So we see it has 2 parts. This one is related to the saddle point, and it's constant. And this one, call it HF, is describes the fluctuations. Okay. So if we look at the partition function, which is so we have the saddle point term, 0, sine e to the minus h. Okay, so now that we have the Hamiltonian of the fluctuations, we want to see their effect, and it would be by looking at the correlation function. We will look at the correlation between fluctuations that are at some distance apart and see if they are related. If they are related, it means that they can cause each other and like enhance themselves. And if they are not related, then it means that every fluctuation is local. Okay, we will also discuss it more. But first, we will diagonalize the Hamiltonian. Okay. So we have again. And we do a Fourier transform. Okay, maybe first I will connect it to what we did last week. Okay, so if you remember, we started with calculating integrals of the form I think it was something like that. Right, and we saw that we have to diagonalize it, and then it becomes just a factorization of independent integrals. So this is what we are going to do here as well. Okay? So the diagonalization is by doing the Fourier transform. Do you want me to do it slowly, or are you sick of Fourier transforms already?
You can just
Yeah, you can pass it.
Yeah, okay. So okay, I'll just write like the big form for once. So this takes out minus IQ minus IQ tag. Yeah. Okay, so when doing the integral, this just gives like the integral over x gives delta q plus q tag, so it becomes can write it also in a more compact way. Where this is the range function. Okay. Okay, so now we want to look into the correlation.
עשינו את זה דיסקרטי, יש סיבה שעשו את זה פה continuous?
In the class?
Yeah.
זה יכול להיות תלוי בתנאי התחלה, נגיד אם היה לכם, אם הייתם נגיד אני לא יודעת מה עשיתם, אבל אתם המשכתם עם ה-XY מודל, עם הגולדסטון מוד?
לא, זה היה חלקיקים בבוקס.
אוקיי, אז אם זה חלקיק בקופסה, אז זה נהיה דיסקרטי.
זה תלוי סיטואציה.
כן, אבל גם באמת זה לא כזה, כאילו זה בסוף אותה מתמטיקה, אותו הכל, זה פשוט אם אתה באינטגרלים או בסכומים. כאילו זה מעבר ישיר. אוקיי, so we looked for the correlation function of this four. Like what is the correlation between perturbation done at some point to what happens at a point distance r. And like if the correlation in physical like situations should decay, this is what allows ordered states. We will see it also later in the calculations that we do. And it also tells about the strengths of the fluctuations. And basically what we are looking for now is what is the effect of the saddle point compared to the fluctuations. So if the fluctuations have small effect, then it's okay to look at the saddle point. It gives like the important physics. But if the correlations are strong, the effect of them is strong compared to the saddle point, then it might not be okay to look only at the saddle point. We will see also this later. Okay.
Before I continue, what is the G power minus 1?
Yes, it's the inverse of the Green's function.
Okay.
It's just a notation. It will come up when we calculate the correlation also, but for now it's just a notation. It makes it look like neater. Okay. נראה יותר כזה נקי.
Okay.
Okay. So, of course, we do Fourier transform. Since in the Q space everything is diagonalized, so everything is easier to calculate. Okay, so now we calculate the variance or the correlation of PQ, which is just okay. So it's 1 over the Q. Let me write the Q. Okay, this is the Q. No, okay, sorry. So the F is integral means beta HF Should I write it somewhere else? Is it like too low? Or is it okay? Okay. So this is
ZF.
yes. Sorry.
No, fluctuation, that's fluctuation.
Yes, it's fluctuation. Okay, so if you can see it, then it's basically diagonalized. So we can just write it as a product of integral. Wait, sorry. It's not with this integral, right? I think I made a mistake. Oh, it is. Okay. Okay, so basically it's a product of all the modes, the partition function of all the modes. So this is the ZQ. Okay, and again, HQ, I'm sorry, it's a bit messy, but HQ is the Hamiltonian of the single mode. Okay, which is okay. Now we do a trick. We actually did it last week. We take the okay. We consider the ZQ. It's just so if we take a derivative by a GQ to the power of -1 of the ZQ, we will get this expression times -2 times beta, right? So we have
Can you give write the definition of the gain function? Can pull it out of the top of my head.
What do you mean? What's a green function? What's a Green's function?
Like the exact definition. I don't remember it.
If you apply the operator upon the Green function, you will get a delta function.
Yes. So here we will also see it, but if you look at the GQ, then it's equate, כאילו, רואים את זה, it's basically the way I defined it. This is the operator. I defined it as g to the power of minus 1 dq, so g minus 1q. So gq gives 1 because it's in the Fourier space. But if we look at the actual operator, okay, it's a bit messy here, but you can show that this is and then you apply it on the Green's function in the real space. We will show it that it's a delta R. We'll see it later. But for now, you can just consider it as some notation that makes it like you see, you can do this trick with it. I couldn't do it if I had this term. You see, so it's just like a function for now. Okay. So we are back here. Okay. So this is just minus 2 divided by beta, the derivative of ln zq. Okay. Okay, so what is ln of zq? I'm sorry, I'm going back here. So by the integrals that we saw last week, it's just square root of 2 pi divided by
Times that.
yeah, thank you. Okay, so we can plug it in. Okay. Okay, so we take the derivative. It just gives 1 over beta. which is this is the definition from here. Okay. So we see it basically proportional to the Green's function. Okay. So the Green's function is related very closely to the fluctuations. Okay. So now we are back to the what we are actually looking for. So we just plug into this what we got.
Why do you choose the zeta to be to the power minus 2?
It's psi.
Psi.
And it basically defines the correlation length. So I think this way the units of this would match the units of this. Yeah, and it's also because I know the answer. I know the physics.
Ah, okay.
Okay. Okay, so now we call this integral I d of r, and we try to estimate that. Okay, so we first take a second derivative of it. This is a trick, you can think of it by yourself, okay? And we put it into here, so we just, since it's a Fourier transform, we Fourier transform the operator, so we get okay, and now we play with this term a little bit. So it's, and I want to get rid of the q square, and so I just add psi. Maybe I'll first subtract psi to the power of -2 and then add it back. So it's -1. Okay. So the Fourier transform of this one is delta r, and this one is just psi to the power of -2 times Okay, so we got this differential equation.
Why did you take the second derivative? I lost it. I'm sorry.
I did a trick.
Ah, okay, it's like the.
This is what called a saddle point. Saddle
No, it's not the saddle point. I calculated the correlation between fluctuations, and then I got this term, and I want to find out what is this integral. So we are looking into the integral. Okay. And this is just a Fourier transform of. I put in the Fourier transform of the derivative. It's the minus q. So, okay. Okay. So now you can notice that this just gives and this ID of GR is basically G of R. So you see that it gives like the identity of the Green's function, that this is the operator and this is the Green's function, and it is probably why you think of doing this trick of taking the derivative.
Although you didn't know it was the Green function before. You didn't know it was the Green function.
Maybe I made the mistake calling it ID, but it looks like the Green's function. It's a transform of something that looks like the Green's function in the Q space. You see? Maybe you mean that I didn't know that this is.
Yeah.
Yeah. I didn't show it here, but with using some tricks, you can see from just looking at the Hamiltonian that this is the Green's function, but I didn't show it.
Okay.
Okay. Okay. So now we have this equation, and when R is not 0, then you can ignore this term. So it's just basically a linear differential equation. So we will solve it now. We are assuming spherical coordinates. Okay, so this operator is okay. So we take this equation, and we get this differential equation.
What's the D minus 1?
It's this operator in the dimension.
Oh, the D there is the dimension of it.
Yeah. Okay. So we want to make an ansatz of what is I d of R. So we do something like asymptotical analysis, if you learned it in Schneer's course. We have this term is with a factor 1, so it's fine, but here we have two terms. We can look at two limits. When R is larger than xi, maybe I start with smaller. When R is smaller than xi squared, then we can neglect the second term, and then we have I. So it means that when you differentiate ID, you get a factor of 1 over R. So ID is polynomial. We will assume that it's something like R to the power of minus P. And when R is larger than xi squared, then this term is the one that is dominant. So the equation is about something like this. And this means that the solution is an exponential, where in each time you take a derivative, you get a factor of 1 over xi out. Okay? So we just make an ansatz that is the combination of these two options and that. Okay. Okay. Okay, so we want to plug this solution into the integral, and from this we will get conditions on R and xi and P that will show how this integral behaves in these regions or similar regions. Okay, so we take the we want to find these derivatives. So if you take derivative of that, we get this. So this A and R minus P, and this is just again ID. So we have okay, so taking the derivative of this term, you get to see R squared ID, and then the 3 plus 1 is from this term. Okay, so we can plug it into the equation and you can see that the ID just drops. So now I'm bringing together the terms that have r squared. Oh. I'm just, yeah, I want to have here ID divided by r, and then have one term which has r in the bottom and one with psi. Okay, so this comes here, the 2p is here, minus this 1, and plus 1p. Okay. Okay. Okay, so we have these terms. This one has r and this in the bottom, and this one has xi. So if you couldn't follow during the algebra, then now it's the actual physics, okay? And also if you didn't, okay, so if we look at r that is larger than xi, it means that we are in a regime that we are very far from the distance between the fluctuations and the point we are looking at is much larger than the correlation length. It means that we should not feel the fluctuation. Okay, so what happens in such a case? Then this term is the dominant one. So we have 2p minus d minus 1 equals 0. Is it clear why? It's because the r is so large, then this term goes to 0 compared to this one, and then the equation is on this one. Okay, so we have p equals d minus 1 divided by 2, and the Green's function, which is the correlation, this way. Okay, so the correlations decay exponentially in a rate that depends on the correlation length, and there is another polynomial decay term, but it's just second order. It's not the important effect. Okay, and the second limit is when psi goes to infinity. And this is what happens at criticality. Okay. Okay, so when psi goes to infinity, then this term disappears. So we look for p plus 1 minus assume p is not 0, and then we get p equals d minus 2. So the arc goes like, when psi goes to infinity, then this is just 1. So we have just r to the power of minus d minus 2. Okay, maybe I'll write it this way. Okay, okay, so what does it mean? So for d, okay, so we have, first of all, we have a polynomial decay, which is much slower. So in general, not related to the specific dimension. At the criticality, the system is much more sensitive to fluctuations, and basically this is how the transition happens. Some small fluctuation can make the system go from the ordered phase to the disordered phase, or the other way around. Okay.
But what if D is like, we're talking about 2D material?
Okay, so so now we go to talk about the dimensionality. So when D is larger than 2, this is just some decay. It decays to 0 at the end. So it's okay. When D equals 2, then it's GR goes like ln R. Which is some divergence, and when D is smaller than 2, then it's like G of R goes like R to the power of D minus 2 in absolute value. So it diverges. Okay. So this is why, specifically for this continuous magnetization model, there is a phase transition only for D larger than 2. So if you look at some systems that is 2D or less, then there is only at t equals 0 there could be an ordered phase. But when you go a bit higher than that, to any finite t, then the fluctuations immediately destroy the ordered phase. So you have only disordered phase. Okay?
D minus 2, is it minus D minus 2, no?
I put it in absolute value because it's
Okay.
okay. Any other question? Okay. Okay, so again, we see here that the effect of the fluctuations depends on the size of the system, and when the effect of the fluctuation is high enough, then there is no phase transition. Okay, so the dimension above which there is a phase transition is called the lower critical dimension. Okay, lower. So here it's the lower critical equals to. So this is something you can see from the Ginsburg-Landau theory. There is something general about the phase. Okay. So right now we looked into the fluctuations. We found the Hamiltonian of the fluctuations and diagonalized it and looked into the correlation between fluctuations and saw from that when they have a strong effect that destroys the ordered phase. Okay. Now we will look into an example of calculating the specific heat, and we will see when the fluctuations have an effect that is higher than the saddle point effect, and then the mean field or the saddle point solution is not valid. Okay. So we will start with the mean field specific heat. The specific heat, if you can't remember your thermodynamics course, is minus T times second derivative of free energy. Okay? So in the mean field, F of M equals M by M squared plus Vm to the power of 4. And we know the solutions are 0 and plus minus square root of A divided by 2b. Okay? So what is the actual free energy? So for the solution of 0 it's just 0, and for M0 these are solutions, we have only the square root of them, so it's the same free energy. And A is A0 times T minus TC. So this is the free energy. And now we can calculate the specific heat of the saddle point. So it's minus T. And
0, right? What did you write in the M0? 01?
M0.
No, the definition of M0, the solution. Yeah, that's 01?
אוקיי, 1 ואז כאילו פתרון 1 זה 0 ואז
okay.
Okay. So okay, this is for of course for T larger than TC, because for T smaller than TC it's just 0. So we have A.
Shouldn't A0 also be squared?
Yes. this is still square, and then the second derivative is just t. Yeah. Okay. Wait. Oh, there is a 2. So, okay, so the specific heat looks this way. It has this growth, linear growth, until Tc, then it drops to 0. Okay, and this is delta S, which is just Tc squared. Okay, so now if you remember, okay, so this is very nice, but it doesn't match the experimental results. If you remember, there is this critical exponent, and in some systems, or many systems, this should diverge. Okay, it means that it should look maybe something like this. Okay, I don't wanna. So now we will add fluctuations, and we will see that they actually can explain this divergence. Okay.
This is for 2 dimensions, right?
The divergence.
The transition.
Yeah, and also for, I think for 3D, you also have this divergence.
Okay.
But the idea is that in some cases there is divergence, and it's not explained here. Here, for every dimension, you have this jump, and then it goes down to 0. Okay. Specific heat. Maybe it's not the right shape. Is this what you meant?
Okay, so the lambda transition, this kind of thing, is usually when the land dominates, right?
The land. Oh. If you need anything in this course, talk to Yosef. He's an expert. So this is for 2D. But there is a divergence in some other dimensions. Okay, we will see that. Okay, so now we want to add the fluctuations. So again, we have where the x is smaller than 0, and this is the fluctuation again. So don't worry, we don't do the Fourier transform again. This is the same Hamiltonian. We just did the fluctuations, okay? Okay, so now we want to calculate the free energy. We will just find the difference in the free energy due to fluctuations, okay? Which is given by this Hamiltonian. So delta F T Okay. Okay, and we are looking for delta CF, which is okay, we have here two dependencies on T. In the free energy, we have this T, and we have psi to the power of -2. I will remind you, we have defined right? So A is A0 T minus TC plus B. So this is, we have A minus 3A, so it's minus am I A, right?
That's 4A.
No, it's so far.
No, it's squared. It's A over 2P squared. Because
No, but it's
No,
square
but
root.
it's square root. Okay. This shouldn't be 6 because I took the 2 out. It was not the smart thing to do. Okay, so it's 2 minus 3. Okay, this is okay. Okay, so this is the dependence of psi to the power of -2 on T. So when we will take the derivatives, if we denote this as, I don't know, I, then we would have, on the first derivative we would have T times I plus I tag, and then on the second derivative you would have
No, wait, but shouldn't it be
yeah, so
I plus TI tag?
I tag, and then when we take the second derivative we would have again I plus T, no wait, we would have I tag plus
2I tag plus
Thank
TI
you.
tag.
okay, but basically we'd have I tag and I tagaim, okay? And you see that every time you take a derivative, then you get a higher divergence, okay? So the most dominant term would be I, and the second derivative of I. Okay, so we will just ignore the T and look for this term, okay? then times the derivative of this. Okay, and then when we take the second derivative, then we have yeah, okay. So delta CF is goes like okay. So we now will calculate the integral approximately, okay, and we will see what, and then we will see what it implies on the physics. Sorry about that. Okay, so this integral could be split into the angular term and the like radial term. So we will just look into the radial term. So we have okay, so we have, when looking at Q, we have two regimes. We have the regime where psi to the power of -2 is larger than Q squared, and in this regime, then only this term stays the psi. Okay, so it would be integral from 0 to the order of magnitude to the part where they are in the same order of magnitude. Okay, so it would be psi to the power of -1 dq. Q would be -1 times psi -4, and in the other regime, then we have only the Q. It's not minus. Okay, so here it will be up to some lambda lambda? Is it lambda?
דלתה גדול.
No. Yeah.
כן.
Wait.
למדה.
Yeah. And the idea is that the Q's represent some wave mode, and at some point you get to a mode high enough to that it gets smaller than the distance between the lattice, okay, the lattice constant, and then you just go back to lower modes. So you have some maximum mode, okay? So here you get okay, so we just have a term psi to the power of 4 minus d, and a term, just some constant of this lambda to the power of d minus 4. Okay, so again we can look at the cases of d smaller than 4 and d larger than 4. So for d larger than 4, this is the important term because this has the positive power. So it means that CF, did I say it? Yeah. So delta CF is some constant. So it's just a constant addition. So if I draw again this T, so it's CSV, then, and this is CSP, and then for D larger than 4, it would just be some addition, constant addition. But for D that is smaller than 4, then delta CF goes like psi to the power of 4 minus D, and psi diverges close to the correlation diverges when reaching the phase transition. Okay, so the correction is something like this. I don't know. So again, we can define a dimension up to which the mean field approach works, and so for D that is larger than 4, there is a small correction. It doesn't change the physics at all. So so it works, but for D that is smaller than 4, the fluctuations have higher effect, and they just change the physics, so you can't use just the mean field approximation. So this is called upper critical dimension. And we have the upper critical equals 4 in this case. And the idea is that when you have higher dimension, then all the microscopic particles, to say, have like, or the fluctuations have more neighbors that like suppress the fluctuations. So this is why the fluctuations are less important in higher dimensions, and you can use the mean field approximation. Okay, so that's it. I basically wanted just to make things a little bit ordered. I hope I managed to do that, and to show 2 examples of how the fluctuations affect the physics. Okay.
Thank you.